In this video, I'll be going over rational functions. So, first off, what is a rational function? To begin, let's look at just a couple of examples of what a rational function is. So 3x plus 1 over x squared minus 1, maybe, or that's an example of a rational function. 5x over 3x squared plus 2x plus 5, that's an example of a rational function. So anything where you have a polynomial function in the numerator and the denominator. Okay, so these are all examples of rational functions. The graph of a rational function, because we have a polynomial expression in the denominator, what that means is that there's an x term in the denominator, and what we've already seen before is that if a denominator has, or a function has x in the denominator, there are going to be places where that function is undefined. So commonly, or I guess I should say always, we have a break in the graph. So a rational function could look something like this. Okay, and what we see is there's a break in the graph right here, and that line, that imaginary line, is called a vertical asymptote. So every rational function has a vertical asymptote. Many rational functions also have a horizontal asymptote, although that is not a requirement for a rational function asymptote. Okay, so in this video I'll be showing how to find these two different types of asymptotes. There's also something called an oblique asymptote or a slant asymptote. So there are three types of asymptotes that we need to be able to find, and then we'll talk about how to come up with the graph for a rational function. So the first type of asymptote is a vertical asymptote. This is to find these are the unique zeros of the denominator for a rational function. So if we have something like this, we need to figure out what value makes the denominator 0. So all we do is we set the denominator equal to 0 and solve for x. So x equals 3 would be the vertical asymptote. When we say unique zeros of the denominator, suppose I had this. Okay, so what we see is that x plus 3 and x plus 3 are common in the top and the bottom. So only x minus 3 corresponds to a vertical asymptote here. X plus 3, if I set x plus 3 equal to 0, what we would say is there is a hole, so the graph has a hole at x is equal to negative 3. Okay, so we'll see more what that looks like here shortly. But that's what we mean by unique zeros of the denominator. So in this example, there would only be one vertical asymptote, x equal to positive 3. For horizontal asymptotes, we want to compare the numerator, the degree of the numerator, and the denominator. So for shorthand, for the numerator, I'm going to write n of x. For the denominator, I'm going to write d of x, so I don't need to keep writing them. So when we make a comparison, the degree of the numerator could be bigger than the degree of the denominator. The degree of the denominator could be bigger than the degree of the numerator, or they could be equal. Okay, so those are the three instances, and again, we're just talking about the degree of the numerator and the denominator. So if the degree of the numerator is bigger than the degree of the denominator, we say there's no horizontal asymptote. The degree of the denominator is larger than the degree of the numerator. We get a horizontal asymptote of y is equal to 0. And then if the degree of the numerator and the degree of the denominator are the exact same, in that case, we use leading coefficients. So for example, if our function was f of x is equal to 3x squared minus 1 divided by 4x squared minus 2x plus 1. Here the degree of the numerator is 2, the degree of the denominator is 2, so because the degree of the numerator and the denominator are the same, we look at the leading coefficients, which is 3 over 4. So the horizontal asymptote would be y is equal to 3/4. Now there's another way we can find the horizontal asymptotes, and we'll discuss that when we actually look at an example. So the third and final type of asymptote we could have is an oblique or a slant asymptote. And these occur when the degree of the numerator is exactly 1 greater than the degree of the denominator. And then we divide the numerator by the denominator to find. So for example, if our function was 4x to the third plus 1 divided by 2x squared minus 5, what we're going to do is we're going to divide the numerator by the denominator because the degree of the numerator is 3, denominator is 2, so there's exactly 1 degree greater in the numerator than the denominator. So again, we'll see how this works in practice when we look at an example. So the steps we want to take to graph a rational function: first we want to find the domain and the vertical asymptote. All rational functions will have a vertical asymptote. Functions have a vertical asymptote. So we're always going to find that. Then we're going to find the horizontal asymptote or the oblique asymptote. Okay, so the rational function may or may not have a horizontal asymptote, and it may or may not have an oblique asymptote. So a rational function always has a vertical asymptote, but it may or may not have the other types of asymptotes. Next, we want to find the zeros of the function. And we do that by setting the numerator equal to 0 and solving. Next, we want to find the X and Y intercepts. Okay, so to find the y-intercept, we evaluate f of 0. To find the x-intercept, we set the numerator equal to 0. So this is in line with what we're going to do in number 3. And then lastly, test points to graph. All right. So let's look at a couple examples and we'll see how this works in practice. All right, for this example, we want to find all asymptotes, the domain, the intercepts, and then we want to graph. And the function we're going to look at is f of x is equal to 2x squared minus 9 divided by x squared minus 9. And wrote that wrong. This should be 2x squared minus 2. Okay, so first let's find the vertical asymptotes. So anytime we have a rational function, it's probably a good idea to factor this as much as we can. So 2x squared minus 1 in the numerator, x squared minus 9 in the denominator, and then we have a difference of squares in the numerator. So it factors to 2x plus 1, x minus 1. In the denominator, we have x plus 3, x minus 3. So we want to see if any of the factors cancel, and they don't cancel. So let's go ahead and find the asymptotes. The vertical asymptote, remember, is what makes the denominator 0. So what makes each of these factors equal to 0? So we're going to have 3 and negative 3. And we write these as equations. We write these as equations because they are lines. So what I'm going to do is I'm going to go ahead and graph each of the vertical asymptotes, one at 3, one at negative 3. Next, let's see if we have a horizontal asymptote. And since the degree of the numerator and the denominator are the same, they're both 2, that means we look at the leading coefficients. So we have 2, and then I have a leading coefficient of 1. 2 divided by 1 is 2. So we have a horizontal asymptote of 2. Next, because there is a horizontal asymptote, that means there is no oblique asymptote. A rational function cannot have both a horizontal and an oblique asymptote. So remember, it will always have a vertical asymptote. It may or may not have either of the other two asymptotes, but if the function has one of a horizontal or an oblique, that means the other type of asymptote does not exist. All right, let's find the domain. Now the domain often corresponds with the vertical asymptote. The only time it doesn't is if any of the factors cancel. So the domain here is going to be everything except for 3 and -3. So writing this in interval notation, we're going to say -infinity to -3, union -3 to 3, union 3 to positive infinity, so everything except 3 and -3. For the X intercept, we set the numerator equal to 0 and solve. Now, because we've already factored this, all we need to do is set each of the factors that have x equal to 0. So x plus 1 is equal to 0. So I'm going to get x is equal to -1. I'm also going to get x is equal to positive 1. So writing these values as ordered pairs, we're going to say -1, 0, and then 1, 0. And then for the y-intercept, we're going to find f of 0. When we plug in f of 0 up here, we end up with -2 over -9, which is just a positive 2 over 9. So what we end up with is 0, 2/9 as the y-intercept. Okay, so let's put this all together. The horizontal asymptote we said was y is equal to 2. Okay. I have some x-intercepts. So 1, 0, -1, 0, and then for the y-intercept I have 0, 2/9. All right, so we have 3 points on the graph. Because this is curving down, it's going to look like this. Now, I don't yet know where the other parts of the graph are. I could have something in this section or this section. Similarly, I could have something in this section or this section. However, I don't know just yet precisely where those values are going to be. So the best thing I can do is pick an x value, like -4, and plug it into the function and see what we end up with. So -4. And then I'm also going to test +4 just to see what we end up with. So f of -4, what do we end up with? When we plug in -4, I get 30 over 7, which is 4 2/7. So what that tells me is that when I plug in -4, I get a positive value that's a little bit above 4 right here. And then let's plug in 4 into the function and see what we get. And we actually get the same thing, 4 2/7. So we're going to be a little bit above here. Now, that's all we really need to do. We just need to figure out, is the graph above or below this horizontal asymptote? So by testing a value that's in each of these sections, I can tell that the graph is going to go like this and like this. And again, because I know the part of the graph is up here, it cannot also be down here because then the graph would not pass the vertical line test. So if I know that for one interval the graph is above the horizontal asymptote, I'm good. I don't need to consider anything below the horizontal asymptote. All right, let's look at a second example. Our function is f of x is equal to x plus 2 divided by x squared minus 4. Again, let's factor when we can. X plus 2 divided by x plus 2, x minus 2. Now what we notice is that we have a common factor in the numerator and the denominator. So what we end up with is 1 divided by x minus 2. Now, anytime a factor cancels, that tells us that we have a hole in the graph at that value for x. So x plus 2 is what canceled. So what this means is we have a hole when x is equal to negative 2. This is also called a removable discontinuity. All right. Moving forward, let's find all the asymptotes. So for the vertical asymptote, remember, these are the unique zeros of the denominator. Only x minus 2 corresponds to a vertical asymptote. So we're going to have a vertical asymptote when we set x minus 2 equal to 0. We get x is equal to 2 as the vertical asymptote. So at 2, we'll draw in the vertical asymptote. For the horizontal asymptote, if there is one, well, this time we'd say that the degree of the numerator is less than the degree of the denominator. So that tells us we have a horizontal asymptote at y is equal to 0. That means there is no slant asymptote. Okay. Next, we want to figure out what the domain is. So on the previous example, we said that the domain corresponds with the vertical asymptote. However, it doesn't always, or it's not always lined up exactly with the vertical asymptote, because we need to take into account both the vertical asymptote, but also the hole in the graph. So the domain is everything except for negative 2 and 2. So there's the domain. For the x-intercept, again, we set the numerator equal to 0 and solve. So we're going to say x plus 2 is equal to 0. We end up with x is equal to negative 2. This is where the removable discontinuity is. So we're going to say that there is no x-intercept here. And then for the y-intercept, we need to find f of 0. And when we do that, we're going to get negative 2/4, which is negative 1/2. So the y-intercept is 0, negative 1/2. So we have a y-intercept right here. All right, so let's figure out what this graph looks like. The best thing to do is to probably plot some points. I'm not going to belabor that fact, but what we'll see is that this graph goes something like this. It gets closer and closer to each of the asymptotes. The graph looks like that. And then we need to consider the hole in the graph. So what that means is at negative 2 on the graph is where we have the hole. And that's what we get. One thing I think I'd like to mention here is something called limit notation. Okay, and so what this means is what is happening as the x value changes. So let's say as x goes to infinity, what's happening to the function? So as x goes to infinity, that means we're looking as we go to the right on the function. And when that happens, well, the value of the function, this curve right here is getting closer and closer to 0. So what we'd say is as x goes to infinity, the value of the function goes to 0. How about this? As x goes to, let's say, 2. Now when we look at this, when x goes to 2, it goes to 2 in this direction, but it also goes to 2 in this direction. So because the vertical asymptote is actually 2. So it looks like up here, as we go to 2, this function is going to positive infinity, but down here, the function is going to negative infinity. So what we'd say is we want to differentiate between what's happening on the right side of that vertical asymptote and what's happening on the left side of the vertical asymptote. So we'd say as x is going to 2 from the right-hand side, we'd say the function, because it's going up, we're going to say that function goes to infinity. And then in the other instance, as x goes to 2 from the left, so this would be 2 from the left-hand side, f of x is going to, because it's going down, it's going to negative infinity. So I want to introduce this limit notation here because these types of questions, the idea of a limit is very common and prevalent in calculus. All right, and one more example. We have f of x is equal to x squared minus 4 divided by x plus 1. Again, let's factor this. X plus 2, x minus 2 divided by x plus 1. None of the factors cancel, so we don't have a removable discontinuity in this graph. So let's figure out the vertical asymptote. These are the unique zeros of the denominator. So set the denominator equal to 0. We're going to end up with x is equal to negative 1 as a vertical asymptote. For the horizontal asymptote, well, in this instance, the numerator is greater than the denominator, so we'd say there's none. There's no vertical asymptote. Let's see if there's an oblique asymptote or a slant asymptote. Well, when the degree of the numerator is 1 greater than the denominator, we do have a slant asymptote. So what we do is we divide. We want to say x squared minus 4 divided by x plus 1. Now, we can do long division to figure this out. The way that I recommend is you do synthetic division. And hopefully you remember this from college algebra. So what we do is x plus 1 is the divisor. So what we're going to do is we're going to divide by negative 1. And then what we do is we take the coefficients of the dividend. So we have a 1 for x squared. Since there is no x term, in other words, this is x squared plus 0x minus 4. So we need a placeholder for the x term, and then negative 4, and then we're going to divide. So how this works is we bring down the positive 1. We say 1 times negative 1 is negative 1, and then we add. So 0 plus negative 1 is negative 1. Negative 1 times the divisor is positive 1. We end up with negative 3. Now what we really care about, this number right here, it's kind of like the remainder. Going to run out of room there. Okay, so we don't need to concern ourselves with the remainder. But the 1 here and the negative 1, those values become the coefficients for the slant asymptote. So y equals 1x minus 1, which is just x minus 1. So this is a slanted line. It has a slope of 1, which is the coefficient of x, and it has a y-intercept of negative 1. So this slant asymptote is going to look like this. All right. Next, let's find the X intercept. This is what makes the numerator 0. Well, 2 and negative 2 are going to make the numerator 0. Write those as ordered pairs. And then the y-intercept, what happens when we input 0 into the function, we get negative 4. So 0 comma negative 4 is the y-intercept. So let's plot these points. 0 comma negative 4 is down here. We have 2 comma 0, negative 2 comma 0. So looking at these values, I know I'm going to have part of my curve over here, and then my other part of the curve is like this.